So I said first, I'm Valerie MASSON-DELMOTTE. I work on past climates using ice cores. So I said to study how the climate system is working, we have three things. Heavy observational networks of the present day. Weather, atmosphere, atmospheric chemistry, greenhouse gases, as you have just seen. That's knowing how the system works today, understanding the processes. We have models. Models are developed from the understanding of the physics, of the biology, of the processes at play, and they are used for the future. And they need to be tested. And for that we have a unique thing, is the realization of past climates and data about past climates. In this lab we work using a variety of archives on the continent, in the deep sea, using sediments in the ocean. And this also requires heavy infrastructures with marine cruise boats equipped with drilling facilities. And we have these ice cores that are extremely precious, and they are unique because you have an information on climate in the polar regions, but in the air trapped in these ice cores, you have an information about the global atmospheric composition. And it's only on 800,000 years that we know precisely the greenhouse gas. Before that, it's indirect, it's more uncertain. Okay? So I propose to show you one lab where ice cores from Vostok, Dome Sea, Drowning Maudland in Antarctica, and ice from Grip, North Grip, and Neme from Greenland have been analyzed. Okay? Machine that is working, and the other one at the back, these are currently working. This one you can touch, no problem. It has been disconnected from the high voltage and everything. So what you see, half of these variations is albedo, half of these variations are past changes in greenhouse gases. And these data are essential to test the new Earth system models that couple greenhouse gas simulations and climate simulations. The only way to make sure you have the right processes, the right speed of changes, the right understanding of the long-term decay of CO2 is using these past climate data. What is being measured on the bottom here? We are focusing now on this period. This period is very interesting. It's about 5 degrees warmer than today in both poles, not necessarily at the same time. This we don't know yet. The sea level was higher by 4 to 6 meters than today. What's the proof? It's that just when you warm the poles for a long time, millennia, you melt the ice sheets. And we know for Greenland the threshold is about 2 to 5 degrees above present day. We don't know exactly the sequence of events, and we don't know also in a warmer world how the variability of climate is affected. So now we have the big picture, and we are refining this by doing measurements 20 years by 20 years. That's the best we can do. In a very dry place, we never have a season, so we are looking 20 years by 20 years on how the variability was affected in a warmer climate in Antarctica. I think I was asked to talk to you today for this interest of past climates, and also because we have a message to give in our ice core community. We need European coordinated infrastructures for the storage of our ice samples. So I show you an example. So these are an example of these samples. I cannot bring you in the cold room with real ice cores. It's 2 by 2 meters, so no way. And it's also minus 25, so you won't go in. But these are samples that were stored in these plastic bottles. So you can see Dome Sea. The depth is this divided by 2, so 1.3 kilometers. And the age is about 125,000 years. Homo sapiens moved out of Africa to the Middle East. Not even yet in Europe, you know.
So you see the footprint?
Not yet. No, we see no human footprint before. There's a debate. There's a debate. People are arguing whether we see a human influence on the atmosphere since the beginning of agriculture a few millennia ago, for instance for methane, or just since the industrial period. But 1,000, 10,000 years ago, no footprint at the global scale. Sorry. So, one-third of the Dome Sea core is stored in Antarctica. It's the best freezer. No risk to lose it. But when you transport it to Europe, when you store it in facilities at the national level, you are never granted that this will be stored as long as it deserves. To give you an idea, coring 2 ice cores, 30 million euros, okay? And the value of these ice cores that are left is much higher because we have analyzed them, we have dated them. If someone asks us a bit of ice of, I don't know, 726,000 years before present, because there has been an inversion of the magnetic field of the Earth at that time, we can give it this bit of ice. So when it's analyzed, it's even more precious. It needs to be stored at -50 degrees, because otherwise you lose gas through the micro cracks. It's extremely important. And for the moment, we don't have a coordinated network in Europe. We have a big freezer in Bremerhaven, Germany. We have another one in Copenhagen, Denmark, and another one in Grenoble, in France. And they are not coordinated, so we submitted last year ESFRI proposal in order to have a European coordinated infrastructure on several sites for the deep ice cores, and also, probably more important, for preserving this very precious information on past climate and environment, not only in central Greenland and central Antarctica, because this is very cold, it's not melting, but on areas of glaciers that are endangered. As soon as you have melting and percolation, you erase the memory of climate and the ice. So there's now a real emergency to do what we call the patrimonial drilling and storage of ice cores from the Alps, from the Andes, from Tibet, from the Arctic glaciers that are all affected by melting. So we need to go to the high altitude sites and drill and store, even not analyze now, but store, because this information is very precious for understanding local changes, for understanding past pollution, and also for new techniques that will be developed to make them speak more. So that's, I think, another reason why I was asked to talk with you. That on our community we have this project and we need support that it will pass in the future and be supported at the European level.
So it's not on the roadmap yet?
It's not on the roadmap. It was well received, but there will not be a new ESFRI call this year, so we need to wait more.
How much money are you asking for?
The thing is not so much the investment, that's the recurrent support. I think what we need is money for the storage facilities with efficient techniques, not to emit more CO2 than necessary. You know, new techniques to make cold rooms. And we need also the access for all countries. Because we have ice core scientists now being formed in new European countries, but we don't have facilities for them to access easily in the cold rooms. So it's the two sides. It's not only storage, it's also having facilities to cut and to sample easily in these cold rooms. You know, for the moment, in Grenoble it's a commercial freezer, so you push the meat, you push the fruits, and you carry your ice core sample, you know.
Do you mind to take one of the...
I can take one out, of course. Okay. So, as I said, we are looking at the rhythm of past climate changes. In Antarctica, the fastest change we have is about 4 degrees in 1,000 years. That's the fastest change. You can compare to the forecast for the future, you know. Compared to what is planned, is slow. And we can also look at abrupt events, mostly in Greenland. And we know the most abrupt changes, they are the warmings. And the most abrupt warmings, they had an amplitude, you know, it's these abrupt instabilities during glacial periods. They have an amplitude of 8 to 16 degrees in 50 to 500 years. So you have a triangle shape, both between glacials and interglacials, and during these abrupt events. It is not understood how it can be so abrupt. It probably involves abrupt shifts in the atmospheric circulation, sea ice, and amplification by changes in ocean currents. Maybe you have seen that result recently. We published that last spring. We have analyzed that at ultra-high resolution the last abrupt events. And we can see that some parameters shift from one year to the next. And these parameters, they reflect the origin of the moisture. It's based on these measurements I mentioned. And it shows that the atmospheric circulation in the Arctic, it's potentially unstable. It can have modes and shift between modes. And that's highly important for the future. And we have compared these ice core results with climate models. Climate models, they underestimate the glacial interglacial changes. Okay, they have the right sign, but they don't have enough amplitude at the glacial interglacial scale. And they clearly are not fast enough compared to the fastest of the past changes. And that's very important. So I hope to have convinced you, in the short time I have, of the importance not only on studying the present day system, but also studying different occurrences, different states and different transitions of the system. And that's complementary to the observations for present day. And that's very important to test if our process-based understanding is correct.